Okay. Right. Um, okay, so we have a pack week this week, so we're gonna start chapter 9 today and tomorrow, and we're gonna take a look at the rotation of rigid bodies. Let me get this. The rotation of rigid bodies. So this is a this is gonna fusion some of the concepts that we'd already discussed about rotation, about energy, and a system of particles, right? So we're gonna see that a rigid body is basically a system of particles for which the distances between those particles are remaining constant along the a long time, right? Let me check the chat box. Aaron, so Aaron is asking if I can post these on Canvas. Yeah, they should be up. Let me just check real quick, but I posted them. Mm. Oh, I uploaded the file, but I haven't posted in the lectures section. Let me just put it now. All right. So now it's on lectures in the section. Sorry. Okay. Okay, so certain objects cannot be represented right as a moving point, as we discussed before, and they rotate about an axis, right? Let's think about an airplane propeller, a disc, whatever, it's rotating along about an axis. So we'll consider objects that have perfectly definite and unchanging shape and size. That's what we call a rigid body, right? So it's basically an ensemble of particles, let's say of tiny, let's say, differential of mass that are not changing the distance between each other. So the whole thing is being conserved, and it's not changing, it's not being deformed, it's not changing shape, right? As the the system is evolving, let's say. All right. Any questions about that? Any questions how we are establishing the model for a rigid body, right? So it's an ensemble of particles that are not changing the distance between each other, basically. All right. So let's take a look at what happens when we are performing a rotation, right? Um, so we're rotating about a fixed axis. Let's say we're rotating about the origin here. So the axis of rotation passes through here, and then we have two more axes, X and Y, as we always, establish in a two-dimensional system. So one way to describe the position of this body over time would be specifying the X coordinate and the Y coordinate. Yeah, but that means that we need to calculate two components of the position of the particle. And as you can recall um, from circular motion, it's easier just to establish an angle, right? So we can reduce those two coordinates to just one, which is theta. So theta will let us know without any doubt, where the whole body is. So this is not just a particle anymore, but it's a rigid body, let's call it. So if all those of the particles or the differential of mass that are composing that rigid body are not changing their distance between each other, so if we establish the angle theta, then we will know the position of all the points of the object, let's say of the rigid body. So instead of considering two, let's just focus on the tip of the arrow, right? If we, instead of considering two coordinates here, we'll just consider theta, and that would let us describe the motion with just one single angular coordinate. We call this theta angular coordinate, right? So it's completely describing the body's rotation. Of course, the body's not moving, it's just rotating about the fixed axis. The arrow is not moving anywhere. The P is not, it's just rotating. That's what I'm saying. All right. So it's quite intuitive, but it's pretty useful because we are just ditching two coordinates, X and Y, to have instead just one, which is theta. All right. Good. So just a quick refresh about radians here. So we talked about radians before. We know that one revolution, one turn is 360 degrees, and that's 2 pi radians, and that's coming from the fact that that's the length of that's related to the length of the perimeter of the circle, let's say, with the radius. So one radian would be the angle at which the arc S is equal to the radius R, right? So the whole rotation, it's 2 pi. And so the angle in radians doesn't really have dimensions, but we write rad, a RAD to distinguish it from degrees or revolutions. But because this is just let's say a relation, right? A ratio between the distance that the particle would be covering, right? When the angle theta is varying, right? And that ratio is basically S, so it is R times theta. So S divided by R, and that's the angle you get. That's the relationship you have between the distance and the angle. So you can see that here you have meters and meters, so you have some dimensionless quantity there, right? Because you're just taking into account this portion of the rotation you're getting for for the distance that it's covered during that motion, right? So just a quick refresh on that. But it's important to remember it because now we'll be working with the angle, not the specific coordinates in an X and Y system for the particle, or let's say in this case, the rigid body. Any questions about this, about radians? All right. All right, so we also talked about before in circular motion about angular velocity. And now we will work a little bit, work a bit more with this and make it more formal, let's say. So let's say we have our coordinate theta, which is the angle that it's being spanned in motion. So it's specifying the rotational position of the rigid body at a given instant, right? And this is resembling what we call X, right? X or Y, let's say, the linear coordinate that we use to specify the position of a particle on a motion, right? On any motion that any of the motions that we have studied, straight line, free fall, which is straight line two-dimensional motion, a projectile, right? So in this case, we're looking at the angle, but the mathematical treatment would be exactly the same, because this is basically a coordinate in mathematical terms, right? So we can describe the rotational motion of that body in terms of the rate of change of theta. Basically the same thing that we did before. So we can define the average angular velocity of the body as the variation of that angle theta over time. So we have the average, just like we did with straight line motion, right? We have the average angular velocity, which is symbolized by omega, right? And this omega will be equal to the variation of the angle theta, which is the angular displacement, let's call it, divided by the time interval in which this displacement is taking place. So I think that you can see what we're aiming to in the next slide, but here we have the graph that it's showing, right? How it's that delta theta being represented here. So if we have the particle at an initial point, let's say 1 at time 1, then this thing is rotating counterclockwise to a position 2 at time 2, and we have two angular positions, let's say theta 2 and 1. So the difference between those two will be the displacement that the position had in terms of the angle, right? And that displacement divided by the time in which that happened, the time interval, gives the average angular velocity. So this is not instant, right? It's not instantaneous. So in the same way that we did before, we can take the limit of that. So if we take the limit of the interval of time going to 0, meaning that we get a very, very small instant, we go to a differential instant, and then we get this d theta dt. So we get the derivative of theta in order to get the instantaneous angular velocity of the rigid body. So I trust you remember when we did this for straight line motion, and actually for any calculation of velocity, right? So we know that velocity is the derivative of position. Position is given here by the angle. So the functional form of the angle derived with respect of t will give us the angular velocity, omega. All right. Any questions about that? So we're treating this theta just as a function of time, which is giving us the angular position of our body. Good. All right. So we have the instantaneous rate of change of the angular coordinate, and that's the instantaneous angular velocity. And we can take a close look at some examples here. So let's say this thing is rotating counterclockwise, meaning that it's going to the left against the clock's rotation. So this theta will increase, because we are always bear in mind that theta will be taken from the axis x to the direction of spanning the direction to the axis y. So our positive variation of the angle theta will be if this thing is going to the left, so counterclockwise, meaning that the average angular velocity will be positive. And then if we take a look at what happens when this goes clockwise, then we'll be spanning a bigger let's call it a bigger angular coordinate into a smaller angular coordinate, because we're going from here to here. And if we're taking the angle from this x-axis, then the displacement will be negative and the angular velocity will be negative. And that's just saying, the fact that this is the angular velocity is positive or negative is just establishing the direction of the rotation that the object has. All right. So similarly to what we have when the velocity is pointing to some direction or the other. Well, the units of this angular velocity is radians per second, and we actually can write that as second to the -1, right? Because basically this is dimensionless radians. Okay. Important consideration is that at any instant, every part of a rotating rigid body has the same angular velocity. Because again, these particles are not changing the distance, the particles that are composing the rigid body are not changing the distance between each other. So there's no change in the body, there's no it's not the body's not being deformed while it's rotating, so all of them must have the same angular velocity. Are we good with that? Any questions about this? All right. So let's take a look at how we define, completely the angular velocity, because so far this is a scalar quantity, right? But that scalar quantity is actually telling us the direction of the rotation. So there must be some other characteristics of it, right? That it will let us define the rotation and without being ambiguous about it, right? Because the fact that you're just giving a scalar, you're getting a number, it's not telling you the direction in which the thing is rotating, right? So as we had before, we had, the velocity is a vector, right? So it tells you the direction in which the motion is taking place, besides the actual speed, right? So the modulus of that vector. So we have the same thing with the angular velocity. And in this case, it will be given by the rule of the right hand. So this instant omega that we calculated before is a z component of an angular velocity vector directed along the axis of the rotation. So if the thing is rotating counterclockwise, let's say, if we take our right hand and cover, mimic that rotation with our palm, with our four left fingers, the ones that are not the thumb, so we will get the direction of omega pointing to the same direction as our thumb, similar to what we do with the vector product, right? And in the case that the thing is rotating clockwise, then we need to cover that span, that angle, that rotation with the other fingers, right? With the big fingers that are not the thumb, and we'll find that the thumb points where the velocity, the angular velocity is pointing, right? So it's applying the same reasoning as a vector product. All right. Any doubts about that? Just cover the rotation with the right hand, and you'll get the direction in which the vector should be pointing. So as a rule, let's call it rule of thumb, we have omega pointing up, pointing to the positive direction. That means that the rotation is it's being counterclockwise. And if omega is pointing down, let's say negative direction of z, then the rotation will be clockwise. All right. So that's how you determine the actual vector of the angular velocity, not just the modulus, right? Not just that scalar. So the angular velocity is a vector, which is determining the rotation of the whole body in terms of the direction and in terms of the intensity of that rotation. Okay, any questions about this? All right, let's continue then. So as we defined position in terms of the angle, then we define the velocity in terms of the angle. So we have angular velocity. And of course, if we define those two, then we can get the acceleration, right? So a rigid body whose angular velocity is changing, remember, acceleration is strictly related to the change of the velocity. So if we have a change in the angular velocity, then that means that we have angular acceleration, right? And that angular acceleration will be taken into account the rate of change of the velocity. The same in the same way as that we did with the other kinds of motion, right? If we have position, then we have velocity, and then we can calculate acceleration if that velocity is changing. So we can, same thing as before, we can calculate the average angular acceleration, which would be the variation of the angular velocity in terms of t in a certain period of t. And so if we take the limit of that, then we get the derivative here. So our angular acceleration, so we're noting this with the letter alpha. This is not an A, this is alpha, the Greek letter. So alpha equals the derivative of the angular velocity with respect of t. So we're taking the function that is giving the rate of change of the position, which is the velocity, and deriving it with respect of t, and that will give us the acceleration. So the acceleration, you can see that it has similarly to the straight line motion, we have radians per second square, and that we can reduce it to seconds to the -2, which is 1/second square. All right, so you can see that here meters are being replaced by radians, right? Because that's how our position is measured in angular quantities. So in terms of vectors, alpha and omega are in the same direction, right? So if let's say they are acting in the same axis, right? So it's the rotation axis. But if they are in the same direction, that means that the thing is speeding up. If it's quite intuitive, right? So this alpha is contributing to the modulus, you know, to increasing the modulus of omega. And if the vector is pointing the opposite way of omega, then that would mean that the rotation is slowing down, and it makes sense because it will be contributing to the decreasing of that modulus. But what would happen if we reach 0 and then we keep accelerating to the other direction? Then if we have this rotating to the let's say left, like here, counterclockwise, then we would reach angular velocity equal to 0 when we get here. Let's imagine that this arrow, green arrow, is being reduced over time, as long as this thing is still acting. And if it keeps acting on that, it will start accelerating it, and it will start increasing the modulus, but now omega will be pointing the other way. So this thing will rotate like this, and it will slow down until it stops, and then it will start rotating the other way, right? So there is a change in the direction of the rotation due to the application of that acceleration. Even though the direction of the acceleration hasn't changed at all, but it's just surpassing that positive direction that omega has, and then turning it into a negative into a negative component for the omega. This is similar. I mean, actually, this is the same, right? It's the same idea of an object moving on straight line motion to the right, which is braking, let's say, which has acceleration pointing to the left. But at some point after reaching 0 velocity, then if it keeps accelerating to the left, then the object will start moving to the left, because then the velocity will be pointing to the left, right? And it's the same idea here. So this thing is rotating, and then once once omega is depleted and started to grow into the other direction, that will mean that the object starts rotating clockwise. All right, so that's an interesting consideration. As alpha is not changing at all, not changing direction, not changing anything. Alpha is remaining constant. All right. Any questions about this? Any questions about the definition of alpha, the angular acceleration? Right. Let's continue then. Okay, so as we've been saying so far, there is a direct, let's call it, correspondence between the straight line motion equations and this fixed axis rotation. So if we take a look at the equations that we had for straight line motions, you can see that those are virtually the same, but with different symbols that are just establishing that we're working with angles, right? So if we have constant acceleration in the linear motion, it's basically the same for the fixed axis rotation with constant acceleration, and we get the same expression. So we can calculate the position as the initial position plus the angular velocity, speed in this case, times the time plus 1/2 the angular acceleration t squared. The velocity, the angular velocity, we calculate it as the initial velocity plus the acceleration multiplied by the time. And of course, we can get the same two equations that let us bypass using time here, and let us bypass using the acceleration here, just the same as in the straight line motion. Because you can think about this as just a change in the actual let's say significance of the coordinate, but the math will be the same, right? So the functional forms of these quantities are the same. The difference is what they're meaning in the physical space. And let me just say that that's not trivial, right? So it's not trivial. The fact that you need to specify your physical framework, right? So you can see both these equations apply. Yeah, great, but they're not describing the same they're not describing the same physical situation. So if there's no physical framework established, the math doesn't mean anything for us. All right. Any questions about that, actually? Because, you know, we care about the physics of what we are analyzing. So math without physical correlation or physical significance, let's say, it's just pointless. All right. Let's go a bit further on this. So let's relate the linear and angular kinematics, right? So now we've established the both basis for linear and angular kinematics. So let's just take a look at this example here. So we have a rigid body, any shape actually, and we are analyzing a point of that rigid body, right? So all the particles that are composing that rigid body are not changing their relative coordinates. So as this thing rotates, all of them rotate in the same way. So let's say point P is a constant distance r from the axis, so it's moving in a circle because this whole thing is rotating about that axis, that origin axis, let's call it. So in order to relate the linear and angular quantities, we can use this relation right here, which we established right at the beginning of the class, which is the distance that is covered at the time this angle is varying, right? So that arc, let's say that arc of the circle, it's S, and it's equal to R, the radius, times the angle. So if we take the derivative with respect of time of a differential of that arc, and then this is displacement, right? So that's displacement. We're taking the derivative of the displacement with respect of t. So this will give us the velocity, right? So this is the tangential velocity that we're getting here. And that's r, which is a constant in our system, multiplied by the derivative of the angular position with respect of t. So this is omega. And then we can write the linear speed of a point on a rotating rigid body equals the angular speed multiplied by the distance of that point from the rotation axis. So basically, I mean, we had this we had this from rotation from circular motion, but now we're getting a more formal definition of it. All right. So that's how we're basically relating the linear quantity v with the angular quantity omega. So you can see that the farther the point is from the axis, the greater its linear speed. And that's a very interesting consideration, right? Because we said that this whole thing, it's rotating, with a constant omega for each of the points or the particles, let's call it, that are creating this rigid body. But the linear speed is not constant along that body, and it's dependent of the radius of the distance that we have from the origin. So a particle, let's say a differential mass here, would have greater velocity, linear speed, than a particle that it's closer to the origin, although they have the same omega. And it's, you know, if you ever done that, if you've ever done that, if you've ever been in a rotating situation, you'll see that you will experiment more velocity if you're farther from the origin of your system of the actual rotation axis, right? And that will we'll see that, and when we get to the concept of inertia, right, and the rotation. But that's for next class. So any questions about this? All right. So same thing we can do with the acceleration, and then retrieve the expressions that we have already talked about for circular motion. So let's just, this is like a quick refresh about that, but this is also applicable to rigid body rotation, of course. And we will get the tangential acceleration as the derivative of the tangential velocity with respect of t. And if you recall the expression that we just calculated, then this will be r times the derivative of the angular velocity, and that's r multiplied by the angular acceleration, right? So you see that the tangential acceleration, similarly to the tangential velocity, is being linked to the angular acceleration by the radius of actually the distance, right? The radius of the circle. So the distance of the particle p to the axis that it's leading that rotation. All right. So this is tangential acceleration. But centripetal acceleration, we had this expression here, and remember we call this like we call that the radial component of the acceleration, which is always pointing to the center of the rotation. And we had that was v squared divided by r, and that's omega times r squared divided by r, and that's simply omega squared multiplied by r. So in the same way as in the circular motion of a particle, we can apply that for each of the particles of the rotation of the rigid body in the rotation. And then we have the components of the linear acceleration. So we have the total acceleration as the sum of the two components of the acceleration, the tangential and the radial components, which are calculated by this expressions here. So the resulting, let's say the net acceleration is this vector here, the net linear acceleration. All right. And you see this is interesting because we're just using one. Again, we're reducing the two components to one single angular acceleration, one singular angular velocity. So in terms of simplicity, it's much more, let's call it simple, right? To reduce the number of coordinates and be able to work with angular coordinates. All right. Any questions about this? All right, awesome. Let's then talk about what happens with the energy in rotational motion, and then I think we will have time to take a look at some problems. Right, so as I said, we think of a rigid body as being made up of a large number of particles, right? An infinite number of particles, which can be the several infinite actually differential of mass, right? That it's composing the body. So we have masses 1, 2, 3, etc. Right? And then we have perpendicular distances r1, r2, etc. for each point of that rotating body, right? Just like we have here. Let's say we have not just P, we have all of the particles that are composing this rigid body, and then we have all the positions that correspond to each of the particles, right? So we have the masses of those and the position of those, which are the distances to the center of the rotation. So the speed of each particle, let's call each particle I, that will be VI equal RI omega, where omega is the body's angular speed. And we know that omega is the same for all the particles, right? Because it's the whole body that it's rotating about the axis. So if we want to write the kinetic energy of the particle I, let's say just one particle, then we can write, what we know, the kinetic energy equal to 1/2 of the mass multiplied by the speed of the particle squared. And if we just substitute V for the expression that we just come up with in terms of omega, then we would have 1/2 of m r squared omega squared, right? So this is just for one particle, but our body has infinite particles. So the body's total kinetic energy would be equal to the sum of each of the kinetic energies of the particles. So that will give us this expression, right? A sum in I for each particle of 1/2 mr squared omega squared. And we can rewrite that in order to get a new term, right, that we're gonna define. So if we rewrite that, let's say we just take all the omegas out of the sum and then put them here, and then we associate all of those terms all together, then we have 1/2 of the sum of m multiplied by r squared multiplied by omega squared. And that we can express it like this. So the quantity here, the sum of all those masses multiplied by the square of their distances to the origin, we're gonna call it the moment of inertia. And it's symbolized by I. And that moment of inertia, you can see it's dependent of the axis that we're choosing for rotation, because that is what will define the R's, right? So the definition of this moment, we will see that in the next class, but for now, the moment of inertia will be defined by this, and it is basically the sum of the masses of the particles that are making up the body, multiplied by the perpendicular distances of the particles to the rotation axis, elevated to the power of 2. So we have that. And you can see that this will have units of kilograms meters squared. And then we can rewrite the rotational kinetic energy, because now we're going to use this word, rotational kinetic. Of course, it's kinetic energy, right? But it's due to the rotation of the body. So we will call it rotational kinetic energy of the rigid body, which is rotating around some specific axis. And that will be equal to 1/2 of the moment of inertia of that body for a given rotation axis multiplied by the angular speed of the body squared, right? Then we will see how we calculate this I, which is the moment of inertia, but you need to remember and take into account that it is dependent of the axis that we're choosing, right? Because it's not the same if we rotate the, let's say, this rigid body about this axis, or if we rotate the rigid body about a different axis, let's call it this, an axis that it's going through here, so it's just in the plane. Let's not, it's perpendicular. Let's say it's not perpendicular to the plane, so it's in the plane. So this thing will rotate differently, and then the r's for the calculation of the, sorry, the r's for the calculation of the moment of inertia will be different, right? And that will change this expression, and that will change I. So I is dependent of the, of course, the shape of the body, but also the rotation axis that we are choosing, right? Actually, the axis that the rotation is taking, it's being performed, in which the rotation is being performed. All right. So we come up to this expression, the rotational kinetic energy, which is, I mean, if you just take a closer look, you'll see that the linear kinetic energy, let's say, it was 1/2 of the mass, the velocity squared, and now we're replacing we're replacing the mass for the moment of inertia, so it's a way to, let's say, weight the masses and the portions of the body that are rotating at specific distances of that axis of rotation. And then we have, of course, the velocity, but now as it's the angular speed, right? It's not the linear. So the expression is quite similar. It has the same let's say physical meaning, but now we're expressing it in terms of the rotation of our rotation system, let's call it, of the angular coordinates in some way. All right. Any questions about that? So of course, a rigid body that's rotating and at the same time is moving, it's having some it's changing its position, it's having some displacement, let's call it linear displacement in any of the axes of our system, would have both, right? Would have rotational kinetic energy due to the rotation, but then it will have linear kinetic energy due to the translation. All right. Yeah. So Nathan is asking, is R not constant? Why can it be taken out of the sum like angular velocity? Well, it's not constant for each of the particles, Nathan. So let me just go back a second here. So if you just stand into one particle, let's say one small portion of your rigid body, then you have a defined R, right? But as you change the particle, let's say we are standing here, what the red dot is, then that R would be different, right? It will be smaller. It's a different one. So it will be changing for each of the let's call it particles, imaginary particles that are composing your system. All right. Cool. So any other questions? If not, let's just jump to the board and let's take a look at a problem. All right. Let me stop sharing here. And get this. All right, let's take a look at set 5 problem 2. So that's my problem two. So this is from this is actually momentum. Let me close this. All right. This let me just read the problem. So it's saying that we have yeah, it says, what is the magnitude of the momentum of a 10,000 kilogram truck whose speed is 12 meters per second? And then it says, what speed would a 2,000 kilograms SUV have to attain in order to have question one, the same momentum, and two, the same kinetic energy? Right, so let me just write the data for this. So this is M equal 1,000 kilograms, V equal 12 meters per second. So we know that P is M divided by V. Let's just calculate the modulus of that. So that's 1.2 10 to the fifth kilogram meters per second. So we're simply multiplying that. Right, so it's pretty straightforward. It's just an application of the of the definition of the momentum. And for part B, we have, let's go like this. We want same P for M equal 2,000. So that's the SUV. This is part one. And part two, it's asking same kinetic energy for mass equal 2,000. Right, so we can calculate the velocity, the speed actually, of that SUV, taking the P that we calculated before, divided by the mass, right? So that's 1.2 to the fifth kilograms meters second divided by 2,000 kilograms. And that's 60 meters per second. You can see that you get the units, right? So you get those out, and you finally get units of speed. So that's for one. All right. And for the other question two, then we need to calculate the kinetic energy of the truck. So you have a truck, and this is 1/2 10,000 kilograms. Let's say velocity squared. That's 720, sorry, 1,000 joules. And then we can we can plug in here for the velocity of the SUV. Let's call it SUV. We can get it from, just working with the expression of the kinetic energy. So that's 2. Let's call the truck here because it's the same. Divided by the mass of the SUV. Root square. So that's 2. That's 26.8 meters per second. That's one. That's the other. And this is the first. All right, so we've calculated the kinetic energy of the truck, and then it's saying that it's asking about the speed for the SUV in order to have the same kinetic energy. So we're using the same kinetic energy here, right? And we're getting the velocity of the SUV, which is 26.8 meters per second, in order to satisfy those conditions. Any questions about this? Oh. All right, good. Let's take a look at problem 3 then. I believe you will go through this one with Kate, so I'll just I think if not, let me check, because I don't want to go, for things double. All right, no, yeah, so you're not going through this with Kate and the discussions. So problem 3, so it says a soccer ball has a mass of 0.4 kilograms. Initially, it is moving to the left at 20 meters per second, but then it's kicked. So after the kick, it is moving at 45 degrees upward and to the right with speed 30 meters per second. Find the impulse of the net external force and the average external force, assuming a collision time delta t equal to 0.01 seconds. All right, so let's see what we have here. We have, and you have a diagram there, but let me just get it again. So we have the ball going at, just using our color V1, and then it's kicked. It goes flying. With an angle of 45. Let's call it theta, alpha, whatever. And it has a different velocity, V2 there, right? And it's asking the impulse of the net external force and the average net external force. Right, so let's write the variables, the constants in our problem. So 0.4 kilograms, V1, 20 meters per second, V2, 30 meters per second. So it's asking about G and the net force. right? We know that J is, say, the net force multiplied by delta T, and that's delta P. Right, so it seems that we need to calculate the momenta for those two situations, right? So we have that for the actual kick. Let me just have it here. The actual kick is taking place at a delta T of 0.01 seconds. So that's the time in which the ball is being in contact with the foot that it's actually kicking it. So we're being asked about the net force that is acting and that it's acting during that kick. So we would, in order to calculate that, we would need to get this, right? Because we have this. We want this. So we can write, say, P1, PI, let's call it PI. PI initial, so that's MV1. That's 0.4, sorry, 0.4 kilograms, 20 meters per second. That's 8 kilograms meters per second. And then we have P final. So after the kick, that's M. So M hasn't changed at all. V2, 0.4, 30 meters per second, equal 12 kilograms meters per second. Is that clear? So this is simply multiplying the mass, the mass by the velocity, by the speed, right? We're just working with the modules of those. But if we write the delta P that we need there, so that vector, we will see that this is pxf minus pxi initial, and the other coordinate will be pyf, sorry, minus pyi, right? So that's the delta. That's the variation of the linear momentum. And in order to calculate that, we would need to use the angle, right? And let's say we have, sorry, I forgot the axis here, y and x. So for the initial portion of it, so for I, we have, let me just write it like this because it's not a problems question, right? So for I, this is p x I, it's equal to minus 8 kilograms per second. Why? Because we see that this thing is going to the left and our positive axis is pointing to the right. So that will give us a negative initial velocity. So it's pointing to the left. And so that component should have a negative sign. And we have y0 equal to simply 0 because we have a motion that it's taking place only on the x-axis. Is that clear? Any questions about that? All right. And for the second part, we have P x final equal to P final cosine of 45. And this is equal to 8.5 kilograms meter per second. Is that clear? Why is it cosine of 45? Basically, because we are projecting it to, we have this, so we're projecting this here. We have the components of both components of the momentum. And same thing for Py final. So this would be P final sine of 45. This is equal to, sorry, this is equal to 8.5, because both are the same for 45 degrees meters per second. So there we have it. We have the delta of the momentum equal to, let's write that, 8.5 minus 8. So that's plus 8, right? Kilogram meters per second. And the other component would be 8.5 minus 0 kilograms meters per second. Right? And then we have calculated J. Because remember, J is the variation of the momentum. And we have the variation of the momentum here. So that is 16.5, 8 point, sorry about that, those 8.5 kilograms meters per second. And that's J. The vector J, right? So we're giving the whole vector. So that's the impulse that it's being applied to the ball when after, in order to get that outcome after the kicking. Any questions about that? Is it clear? So we calculated the momentum for each of the stages of the, first of all, we established the stages that we're looking at, right? We have this I stage, first stage, let's call it, and the second stage, initial and final. Then we establish the actual expression that it will let us get that delta P, that delta vector, and then we calculated each of the components of those vectors for each stage of the motion. And finally, we got that delta P, that vector, which is equal to J up here, to the impulse. All right. If there are no questions, let me just move on to the, I was asking about the force, right? Yeah. So now we have J, we have the impulse, which is equal to, let's put it this way, Jx, Jy, right? Both components of the vector. So we know that that is equal to the net force in x multiplied by delta t, and the net force in y multiplied by delta t. Right? Because that's the actual definition of impulse. And so we're looking for the net force, right? So we want this components here. We want these in order to get the net force. So the net force would be net force in X, net force in Y, and that's Jx divided by delta T, Jy divided by delta T. And that's simply, let's just use these, the two components that we calculated before, right? And the delta T that's given as previous information. So we know that the kicking, it takes place, the force is being exerted for that time. So we have impulse over time. So that's 16.5 divided by 0.01, 8.5 divided by 0.01 newtons. And that's 1,650 and 850 newtons. And of course, we can calculate the full net force. Let's call it F net here with simply just doing Fx squared plus Fy squared, right? So this is 1,856 newtons. All right, but this is not finished because we have the modulus. I'm sorry, I'm taking a couple of more minutes, but I just wanted to have to round this problem and have it nicely done. So you have it. So we have the modulus of the net force, right? But we don't have the angle, so we know it's a vector, so we need the angle, right? And this thing won't be complete until we give that, right? So in order to calculate that, we can do simply Fy divided by Fx. Just, bear in mind that I just ditched the sum, right? Those sums in order to be just less messy with the writing. So that's the tangent of the angle. Let's call it alpha. And so alpha is the arctangent of Fy Fx. And that's 27.3 degrees. So we can say that the force that the foot exerted on the ball was F with an angle of 27.3 degrees with a, let's say, intensity of 1856 newtons. And this is how we are giving the full answer for this. Okay. Any questions about this? Just notice that we've worked a lot with the components, right? We've worked a lot with the vector quantities. And that we'll see it a lot when we're working with momentum and with rotation, right? Because this is getting a little more complex than just a straight line motion. Although we have two straight line motions in this problem, but you need to take into account the way that's being that those momenta are being decomposed in our system of reference. Any questions about this? If not, we can call it for today, and tomorrow we will finish chapter 9, rotation, and talk about inertial moment. And Let me stop here. If there are no questions, stop.